Now, if we want to get, say, the equation of this temperature, okay? So if we want to know the temperature as a function of time, okay? What kind of information do I need to know? Well, I'm going to need to know that I've got an initial condition, but that won't be enough, will it? Okay, I've got to know how quickly, how much this is stretched out or compressed, right? How quickly does it go towards 22? Okay, so in situations where you've got like growth or decay, like radioactive materials, what kind of extra information do they give you that lets you work out that? Sorry, say that again. Yeah, they'll give you, say, for instance, it takes such and such an amount of time, and then after that time has elapsed, you'll have this much of your quantity. So that's what a half-life is, right? Or in situations which aren't like radioactive decay, they'll say, you know, in the year 2000 we had this many people, that was the population. And then 10 years later, in 2010, the population was this much, okay? So in other words, you need two fixed points, okay? So let's say, I don't know, what would you guess the temperature is after 5 minutes, say? Boiling water, 22 degrees is the ambient temperature. What do you think? 5 minutes. 5 minutes. You'd be surprised. I mean, drinkable water from boiling, right? I mean, drinkable water is like, I don't know, the hottest you can get out of the tap generally is about 55 to 60, I think. And you can sort of, is that higher or lower than you'd expect? Higher? I think you can sort of drink that. So I'm going to call it, after 5 minutes, put it up here. Let's get it to 60 degrees. Let's just call it that. Okay. So what's that going to give us? That means we've got 1 point for scale here. Okay, so I know how stretched out or compressed I am. So again, watch out for your scale. Since I've said 60, and I put 50 here, so I guess my 60 would be somewhere up here. What that's going to correspond to is a point on your graph, which should line up with 5. 5 minutes, t equals 5. Okay, now, all of this information now is enough to work out our temperature as a function of time. We're going to do that, but I want to get a few other questions as well. I'd like to know the rate of change, that's this dt on dt business, right? I'd like to know that as a function of the temperature. Okay, that's what we've been doing so far. This is kind of what we guessed at, but we saw that that broke down. Okay, so this is evidently not the way to go. Okay, so if it's not the way to go, what is the way to go? And lastly, let's just apply it. Let's say, I don't know, how long will it take, given all of that, to get to, say, 30 degrees? How long will it take for it to drop down to that far? Alright, let's have a go at 1. Now, this is still something like an exponential equation, right? So t is still going to have this t, actually I'm going to not call that t naught. I'm just going to go back to A. It still has this decay characteristic shape to it, okay? But what difference does this asymptote make, algebraically speaking, to our equation here? How would you adjust it? Any suggestions? If we took off this asymptote, right, this 22, and we called that the actual axis, called that the time axis, okay, then this would be okay, right? So all I've done really is just taken this decay shape and I've just shifted it upwards. You see that? It's the same idea. You could say I've shifted it horizontally as well. They amount to the same thing. So if I want a vertical shift, if you've got a graph, right, like say y equals x squared, and you want to put some vertical shift on it, how do you adjust it? What do you do? You just add a constant, right? For instance, x squared, you want to move it up 10 units, you just say plus 10. That'll do it, okay? A better, more precise way of saying it is to put the 10 on the other side, right? Because that connects the shift to the y value, right? So because it's negative, it goes up. You remember how it's reversed? Anyway, so what am I going to do here? Okay, well, I'm going to add on what I need to get up above, right? So that I'm going to approach 22 instead of 0, okay? So I'm going to put 22 there. Can you see how that works? Can you see how now this is going to obey what we actually want for our sort of limit condition, okay? As t approaches infinity, what happens to this guy over here? Well, this is going to become minus k over really, really large number. So this is going to shrink off into insignificance, okay? And what you'll then be left with is your 22, right? So this is going to work for us, okay? But I still have all of these guys to worry about. How am I going to work out these constants? What will I use? Good. In fact, my fixed points, plural, because I'm going to need both of these, right? So usually, I mean, because it's at the start, let's start with the initial condition. So when t equals 0, the actual temperature is 100 degrees. Okay, so let's substitute it in. Left-hand side's 100. So far, so good. E to the power of 0 is just going to be 1. So here, I'm going to be left with A. Okay? And then with this 22, it's going to go over the other side, and I'm going to be left with 78. Okay? So you can see here, by the way, why I caught myself. This coefficient here is not T naught. Not very helpful to call it T naught, because you're not starting at 78 degrees, right? The starting temperature is kind of made up of this part and this part together, right? There's A, okay? Let's work out K. We're going to use our other fixed point now, right? So when T equals 5, the temperature is 60 degrees. Thank you. So I'm going to bring it into what I already know, which is 60, that's my left-hand side, is 22 plus, I don't have to write A anymore, I can say what it is, 78, e to the minus 5k. Okay, so do a bit of simplifying. This is going to go over and become 38, right? Then I guess I'll divide through by 78. 38, 78, they're both even. So I can write that as 19 on 39. You happy with that? Is that okay? Convert it to a log equation. So this is going to be minus 5k equals log of that number there. And I just want k on its own. Now, could you simplify this? Could you put the minus inside or change the 5, whatever? Yeah, you could, but I think this is going to be enough. Eventually, we're just going to stick this into our calculator. All right? So there's my k. Therefore, remember the point was to get temperature as a function of time. I've gotten rid of all my other constants now. So I can say the temperature is 22 plus 78 e to the this mess. Okay? Be careful with your brackets, please. There it is.